Hi everyone, we are Group 1 from SSCE1793 Differential Equations Section 34. Here are our group members. Today we are going to bring to you applications of first-order ordinary differential equations mixture problems. What actually is first-order ordinary differential equation? Differential equation DE refers to any equation which contains derivatives. It is generally used to express the relationship between a function and its derivatives. There are two categories of DE, which are ordinary differential equations ODE and partial differential equations PDE. Ordinary differential equations ODE contains one or more dependent variables with respect to one independent variable. Here are some examples of ODE, where y acts as dependent variable and x acts as independent variable. First-order differential equations, the power of the derivative of the highest order is 1 and can be expressed by dy dx equals to fxy. Here are some of the examples for first-order differential equations. Next, first-order ODE is an equation that involves fyx with the highest derivative in the equation being the first derivative of y. There are a few types of first-order ODE, which are separable, homogeneous, exact, Bernoulli, and linear. What is a linear differential equation? Linear differential equation is where dependent variables and their derivatives are of degree 1 and each coefficient of the derivatives depends only on the independent variable. Here is the general equation of a linear differential equation, where the coefficient of derivative must be 1 and it has to be positive before pxy. Here is the method of solution for linear differential equation.
Let's analyze the main concept of the mixture problem to get the equation. Initially, consider a tank which has V0 liter of solution that contains A gram of salt. Another solution with B grams of salt per liter is poured into the tank at a rate of E liter per minute. At the same time, a well-stirred solution leaves at a rate of F liter per minute. The problem is to find the amount of salt in the tank at any time t, that is Q. The rate of change of Q equals to rate of flow in minus with rate of flows out for the amount of salt. To calculate the rate flow from information given in the problem, these two formulas are used. The salt enters the tank at a rate of B multiplied with E grams per minute. To determine the rate of salt leaves the tank, we first need to know the volume of solution in the tank at any time t, that is initial volume plus with added minus with the removed volume. Next, the concentration of salt at any time is amount of salt divided by volume of solution at any time of t. Then, to get the rate of salt leaves the tank, we multiply the concentration with F, rate of solution leaves. Finally, we substitute both rate in and rate out into the equation and arrange it in general form of linear equation. The problem statement is a tank contains 40 liters of solution with 2 grams of salt per liter. Salt water containing 3 grams of salt per liter runs in at a rate of 4 liters per minute, and well-stirred mixture runs out at 2 liters per minute. Find the amount of salt in the tank after 15 minutes. To solve this problem, we first list out the information given, V0, B, E, and F. Then sub the values into the equation as shown and simplify it into general form of linear equation. Determine PT and QT. Next, calculate the integrating factor. Write the equation in this form. Given the initial condition, tank consists of 40 liters of solution with 2 grams per liter of salt, so we have 80 grams of salt in it. Use this Q0 to find unknown constant C. We get the final equation of QT. The problem is to find the amount of salt in the tank after 15 minutes. Thus, we substitute the T with 15. We get Q equals to 187.14 grams of salt.
In conclusion, the rate of change of the amount of substance can be represented by a linear ordinary equation, which is like what we have explained just now. The solution that flows in and flows out might have different rates of flow, so they are taken into account in the equation. We also assume that the mixture that flows out is well stirred, thus the concentration of the substance that flows out is represented by the amount of substance remain at time t divided by the volume at that time. By integrating the differential equation, we can find out the amount of substance. For example, salt remain after a period of time. We can also predict the time needed for the substance to reach a certain amount. This equation enables effective interventions and optimizations in industrial processes and environmental management. I hope we have explained the application of differential equation on mixture problems very clearly. Thanks for watching this video.